Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this problem, we have a piece of metal with a work function of 2.2 electron volts and light hitting the surface with a wavelength of 280 nanometers. Note that this is in the ultraviolet region of the electromagnetic spectrum, so it's actually not visible to us, even though I've drawn it in rainbow colors. This light is composed of multiple photons, each with the same amount of energy, a very particular amount of energy. If you remember the equation for this, for the energy of a single photon, is dependent on its wavelength, where h is Planck's constant and c is the speed of light. When a photon strikes the metal, it will transfer all of its energy to a single electron. If the energy is great enough, the electron will overcome its interactions with the metal and become ejected from the metal. Here's a drawing of what that could look like, where this is an empty space where the electron was, and now it's become ejected. In this problem, we want to find the de Broglie wavelength of such an electron. In this problem, we're going to use two main equations. An equation for the de Broglie wavelength, which is dependent on momentum, and one on the conservation of energy. As follows, I will explain why. So what does this problem assume? First, it assumes that the electron will have a de Broglie wavelength. And from the de Broglie wavelength equation, we know that the only way an object can have this is if it has a non-zero momentum, p, which means that the electron must have velocity. So when it gets ejected from the metal, it's going to fly off it like a wave with some velocity. Another thing we're going to assume about the problem is something about the conservation of energy. By the conservation of energy, we know that the only way an electron will have enough energy to fly off the piece of metal is if the energy of the photon will not only have enough energy to give the electron to overcome its interactions with the metal and get ejected, but also for it to have enough leftover energy for the electron to fly off the metal. In this problem, it is assumed that the electron will have enough energy for both cases, for it to get ejected and fly off the metal. In this problem, we are given the work function of the metal, which is the maximum energy required to eject an electron from the metal. And we can easily find the energy of a photon given this equation right here. We know its wavelength. With both of these, we can find the leftover energy, in particular kinetic energy, that gives the electron momentum. So this equation over here must be true. The energy of a photon must be equal to the work function of the metal, the energy used to eject the electron, plus the kinetic energy of the electron once it leaves the metal. But since the work function gives the minimum amount of energy required, while the energy of the photon is an exact value, what does this mean the kinetic energy must be? It must be a maximum. The maximum amount of kinetic energy the electron can possibly have. So that's why I put a max right here. So K max equals the energy of a photon minus the work function. I'm just rewriting the equation right here. So let's look back to our de Broglie wavelength equation, because this is in the end what we want to end up with. So how are we going to get here? Of these three variables, what do we have and what do we not have? Well, we know h. H is Planck's constant. M, that's the mass of an electron, which is also a constant. But we don't know the velocity of the electron, so that's what we need to find. But here, we know the kinetic energy of the electron, because we can easily find this, just calculate the energy of a photon. We know this, and we know the work function of the metal. So how can we relate this to the velocity of the electron? Well, by definition, kinetic energy is defined by the velocity of the object, by 1/2 mv squared. So we can equate this to 1/2 mv squared, where the mass is the mass of an electron, the velocity is a maximum. Because in order for the kinetic energy to be at a maximum, our only variable here, it must be a maximum as well. So now we're going to want to solve for the velocity. But first we should plug in the energy of a photon. And so this is what we will get for the velocity. Now we can plug the velocity into the de Broglie wavelength equation here to finally find the minimum de Broglie wavelength of an electron. And then this can be just simplified. And now what's left is we need to plug in all of our values. The constants, like Planck's constant, the mass of an electron, and our known values as well, such as the wavelength and work function of the metal. So what are our constants? Planck's constant, I'm going to write this in blue, is 6.63 times 10 to the negative 34 joules times seconds. The mass of an electron is 9.109 times 10 to the negative 31 kilograms. And the speed of light is 3.0 times 10 to the 8 meters per second. Okay, so we have those constants. But we have a discrepancy. Our work function is in electron volts, and Planck's constant is in joules. So they're both units of work. We need to convert one to the other. And the easiest would probably be to just convert electron volts in the work function to joules, because the work function only appears once in the equation, while Planck's constant appears twice. And in the end, the units of energy should cancel out to get a wavelength. That's in units of distance. So our conversion factor is this. 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So now we plug it all in. .63 times 10 to the negative 34 joules times seconds. 3.0 times 10 to the 8th meters per second divided by the wavelength, which we're going to convert from nanometers to meters so that things cancel out like the speed of light here. And that will be 280 times 10 to the negative 9 meters is equal to 280 nanometers. Minus 2.2 electron volts times our converting factors. Times 10 to the negative 19 joules per electron volt. Okay, so that's what we get. You can calculate this out, but first we should probably check units to make sure they come out in units of distance. This should be a little bit closer. So what we can cancel out here is this. Meters, seconds, electron volts, and then this is just equal to joules, so we'll have joules right here. Oops. Yeah, so this whole bracket, inside the brackets, will be joules. So we want to convert joules into the basic unit so that we can in the end cancel out and get some other metric. We can work backwards to find this out if you can't recall the units for the basic units for joules. Joules is a unit of work. And work equals force times distance. And force equals mass times acceleration. So the basic units for work is kilograms for mass times meters per second squared for acceleration times meters for distance, and that equals kilograms times meters squared per second squared. So that's the basic units for work. So in the denominator, we will have kilograms times all of this. So that'll just be kilograms squared times all of this. And the square root of this, since all of this is square rooted, is just going to be to the power of 1 kilograms times meters per second as our denominator here. And joules times seconds will be this times seconds. So we'll have this power cancel out, and we'll get kilograms times meters squared per second. Then this will cancel out, this will cancel out, this will cancel out, and we get meters. So that is correct for our wavelength as the unit of distance. And if you calculate this out, you will get that the wavelength equals 8.2 times 10 to the negative 10 meters, which equals 0.82 nanometers.